Okay, so it got disconnected. So we were discussing about the one second. Yeah. So we were discussing about the projectile motion, and so using the basic formulas of the projectile motion, we got the time of light is our 2v sine of theta divided by g, and then we can find out the horizontal distance traveled in air. Distance traveled in air, that is nothing but our range, that is r, and that is our v square upon g sine of 2 theta. That's the basic formula for our this projectile. Now we come to our second part, that is our when it is going to make an impact. Okay. And for that, first of all, we are going to find out what will be the velocities just before the impact. Velocities just before impact, and here we are talking about point B. Okay. And for point B, we can just suppose this is our point B, and just before impact, we know that our this will be a vertical component and this will be our horizontal component. Therefore, we can write this as our Vx minus just before impact, that will be same as our V cos of theta, because horizontal component throughout the motion, projectile motion, remains same, and V this just before impact negative will be our V minus V sine of theta, because direction changes. Okay. Now we come to our impulse during impact. Okay. Impulse during impact, and it is given that it is a perfect elastic inelastic vertically. Okay. Therefore we can say that collision is perfectly inelastic vertically. Therefore we can say that the vertical component just after the impact will be equal to 0. So we can say just after the impact, Vy positive will be equal to 0. And now we can find out the vertical impulse, or we can say the normal impulse. Vertical or normal impulse, and let us call this as our J of n. Then J of n will be the mass into the difference in the velocities, that is after impact minus before impact. And after impact the velocity is our 0. Therefore we can say that our this vertical impulse, that is our J of n, will be equal to our minus of minus will be giving us plus, that is mv sine of theta. And similarly we can find out the horizontal or frictional impulse. horizontal or frictional impulse, and let us call this as G of F, and that will be equal to our friction and our normal impulse, coefficient of friction. Okay. And we substitute our J of N, so we get our horizontal will be equal to our mu mv sine of theta. Now we can easily find out from these two relationship what will be the horizontal velocity just after the impact. Horizontal velocity just after impact. Let us call this as Vx positive. And for that we can use the relationship that our mass into Vx positive will be giving us mass, that momentum just before the impact minus the momentum that will be lost because of the impulse. Okay, so we can use the momentum equation, and we can easily substitute our G of F. So here we get this as m. V of x we also know is our, that x component just before impact is our same, that is not going to change, that is V cos of theta. So this will be coming as V cos of theta minus this comes as mu mv sine of theta, and we can cancel out this mass throughout. So we get this as Vx positive, V can be taken as common, so this comes as our cos of theta minus sine of theta. Okay. Now after impact at point B, it will be sliding and finally coming to rest at point C. Okay. Now we come to the sliding portion on the ground. Okay. And so you can say sliding on the ground. And from, because there is a friction and the coefficient of friction is our mu, so we are going to get a frictional force in the opposite direction, and let us call this as F. So you can say the frictional force that is F is equal to mu mg. And obviously it is a deceleration because ultimately it's going to stop. Okay. So we can say that our deceleration, if represented as A, and that will be equal to our mu times g. This we can easily see from this relationship because force is equal to mass into acceleration. And we can find out the final velocity. Okay. So at point B, just after impact, this velocity is Vx positive, and at C obviously it is going to stop, so let us suppose this final velocity is Vf, which will be equal to 0. So we can use the relationship that our Vf square minus or equal to rather, we can say this as Vx positive square minus 2ad, okay, and d is the distance between the two. And we know that our Vf is equal to 0, therefore we can say from here that our d will be equal to Vx positive square and divided by 2 mu g, because A we know is equal to our mu times g, and therefore we get that our d will be equal to V square, and this is our 2 mu g, and V positive we just calculated is our cos theta minus sin theta whole square. Here I missed mu, so this will be also mu, and this comes as our cos theta minus mu sin theta whole square. Okay, so this is our distance. Now we need to find out the total horizontal distance. You can say our total horizontal distance. Let us call this as capital D of theta. That will be equal to R plus D. So this gives us that D of theta will be equal to V square upon G sine of 2 theta plus V square upon 2 mu G, and we have this as cos of theta minus mu sine of theta whole square. Okay. And this is our d theta, total horizontal distance, and we have to maximize it. Okay. Therefore, you can say maximization and here this v square by g we can take as common. So let me rephrase this equation. So we can write d of theta is equal to v square by g, and this comes as our sine of 2 theta, and this will be plus 1 upon 2 mu cos theta minus mu sine theta whole square. So we can just for the time being ignore this part. So we are going our trigonometric identity. Okay. And for that, let us assume that this function is our f of theta. F of theta is equal to sine 2 theta plus 2 mu cos theta minus mu sine theta whole square. And we are going to solve this equation, and let us expand the square and use the trigonometric identity. First will be about 2 sine theta cos theta plus 2 mu. We are going to get this as cos square theta plus mu square sine square theta minus 2 mu cos theta sine theta, and we are going to multiply it by our this 2 mu. So we get this as about 2 sine theta cos theta plus this comes as 1 by 2 mu cos square theta plus this will be 1 by 2 sine square theta, and it will be our minus will be our mu cancel cos theta sine theta, and these two terms we can combine them, and this gives us sine theta cos theta plus cos square theta divided by 2 mu plus mu is left here because it is square, and this comes as our mu by 2 sine square theta. So this is our f of theta. Now we are going to maximize it, so we are going to differentiate it one by one. So let us differentiate our first function, that is sine theta cos theta, and so this comes as a df of theta upon d theta, and first function will be giving us cos square theta minus sine square theta minus sine square theta, and second function will be giving us minus 1 upon 2 mu. This will be 2 cos sine theta, okay. And this will be giving us 2 cos theta sine theta, and the last term will be giving us plus, this will be mu by 2, and this will be giving us 2 sine theta, and this will be our cos theta. So here this 2 and 2 cancels out. Therefore, we get from here that cos square theta minus sine square theta, and we can take sine theta cos theta common from these two. So this will be plus sine theta cos theta mu minus 1 upon mu, and obviously equal to 0. Okay, and furthermore we can also sort it out by using the identity cos square theta minus sine square theta is equal to cos of 2 theta. So from this we get cos of 2 theta plus, and sine theta cos theta, we can write this as 1 by 2 sine 2 theta, okay. And mu minus 1 upon mu is equal to 0. Now we are going to solve it for this our theta, okay. So let's divide this entire equation by cos of 2 theta. So we get this as our 1 plus 1 by 2, and we have this as tangent of 2 theta mu minus 1 upon mu is equal to 0, and therefore we can write this will be equal to minus of 1, and this gives us that tan of 2 theta will be equal to, this will be minus of 2 mu minus 1 upon mu, and we can write this as our 2 mu, and this will be 1 minus mu square. And we know the trigonometric identity that tangent of 2 theta is equal to 2 tan theta and 1 minus tangent square theta, okay. So we can say this is equal to 2 tan theta 1 minus tangent square theta. So we can just cancel out 2 and 2. Therefore, if we solve this is quite simple to sort it out. It's not much of problem. So let me write it out. So we are going to get this as, okay, let me first of all write this, mu 1 minus tan square theta is equal to 1 minus mu square tangent of theta, and this will be giving us that our tan of theta minus mu times mu tan of theta plus 1 is equal to 0, okay. And so one of the physically possible solution will be equal to this one, okay. So we can say that our tan of theta is equal to mu. This gives us that the maximum, because we differentiate, so we can say theta max will be equal to our tangent inverse of mu. Now we can find out the maximum total horizontal distance, because we are going to put tangent of theta is equal to mu. So we can say the maximum horizontal distance, and for distance, that is our tangent of theta is equal to mu. And Based on this, we can write our sine of 2 theta is equal to 2 mu 1 plus mu square, and we get this as cos of theta minus mu sine of theta will be equal to 1 minus mu square and 1 plus mu square under square root, and we substitute it into d theta. So we get that the maximum value of our distance, okay, so it is, okay, so we are going to substitute this equation, and we can just straightforward write the result. It's only the calculated part. So we are going to get this as v square upon 2g and 1 plus mu square divided by mu. So this is the maximum value of our distance, okay, that was asked for. Okay. So this was the first question. Now we come to the second question. In this question, it states that at time t equal to 0, a massless bucket contains a mass m of the sand. The bucket is attached to the fixed wall by a massless spring that exerts a constant tension T, independent of its length. As in figure, we will see the figure later on. The bucket rests on a horizontal frictionless surface, and its initial distance from the wall is L. The bucket is released from rest and begins moving toward the wall. During its motion, sand leaks out of the bucket. Let x denote the instantaneous distance of the bucket from the wall. Let m of x be the mass of the sand remaining in the bucket at position x. The sand leaks at a rate which is uniform with respect to distance and not time, according to dm by dx is equal to m upon L. Since the bucket moves toward the wall, dx will be less than 0, and hence dm will be also less than 0. Based on this, we are going to two parts rather. Determine the kinetic energy of the bucket, that is of the sand remaining in it, as a function of distance x from the wall. Also find the maximum value of this kinetic energy. And part B, determine the magnitude of the momentum of the bucket as a function of x. Also find the maximum value of this momentum. So in this case, the question is not lengthy, but it's quite simple. It's stating that we have a wall and a surface is there, and on this surface we have a bucket. Okay, suppose this is a bucket, and to this bucket a spring is connected, okay, and its spring, it says it is for tension is a constant, it is independent of the length. Okay. So we can just say that it is a fixed string whose tension is given as T, and this is at a distance of L for the start, and this bucket as a whole, it carries a sand. So at it start moving, the sand start to fall down, and this rate is dependent upon the x. Okay, the rate of this falling of the sand is dependent upon x. So this is dm by dx is equal to m upon L. Okay, so we have to remember this thing particularly. And so let us assume that it's the coordinate of this wall is suppose at x equals 0, and this finally will be x equal to L, and at one particular moment we can assume that which is at a distance x, here the mass left is our m of x, for which particular equation we are going to solve, and then we can just generalize the result. Okay. And we have to remember that this distance x will be decreasing with time. Okay. So at any position x, the mass we have taken is m of x. So whatever relation is true for m of x, that we can generalize for either x equal to L, or we can write it for x equal to 0 also. So that is quite simple. Okay. So here we have to remember that the mass reduction in the mass of the sand is basically a function of the position. Okay, so we can say that our mass as a function of position. Here mass is only the mass of the sand, bucket is massless. So mass is as a function of position. Okay, so which is given as dm by dx is equal to mass oblique the length. Okay, so it means the mass is decreasing linearly with distance and it is not decreasing with respect to time. And if we integrate this equation, so we can write that based on this we can get the equation that our m of x will be equal to our m of L times x plus c. And now we can use the initial condition. Initially the bucket was at a distance x equal to L. So we can write that for initial condition we have that the mass at length L is total mass m, and therefore we substitute it. We get this as our m is equal to m upon L, and value of x is also our L, and plus c. So L length cancels out. So this gives us that the integration constant is equal to 0. So it means the mass at a distance x that we are calling as m of x is equal to our mlx. And so in this case, because x is also a length and L is also length, so we can use this in terms of ratio. Let us write this ratio is our z. Okay, so we can write this is m into z, and with this z is equal to our x upon L. Okay, because this is a simple ratio. Therefore, we can write that our m of x is equal to total mass and divided by this ratio, that is our z. Now we come to our actual equation of the motion. And there is only horizontal motion and horizontal force is there. So we can write this as a equation of motion. And the only force that will be acting, horizontal force rather, will be the tension T. Okay. Therefore, we can say that equation of the motion, we can write a general equation also. Summation of the forces in x direction will be equal to our mass at our x and into acceleration, that is its double derivative. Okay. And this horizontal forces summation is only tension T. Therefore, we can say tension T, and we can put our this m of x will be equal to our m x upon L, and we have double derivative of the distance. Okay. So this is our tension T, and then we can express the acceleration in terms of our velocity. Okay. So you can say that we have our acceleration, which is our distance double derivative, which is nothing but our dv by dt. And this dv by dt we can represent by using the chain rule. So we can write it as dv by dx, and this comes as a dx by dt. So we get this as our v, dx by dt is our velocity, and this is dv by dx. Therefore, we can say that our acceleration x will be nothing but our velocity, and with respect to our product of velocity and the derivative velocity with respect to distance. Now we can use this relationship in the tension T. Therefore, we can say tension T will be equal to our mass into distance times x, and we get this as V dV by dx. And we rearrange it because we are interested in using the this, we get V times dV is equal to tension L, and we have this as m, and this comes as a dx upon x. Okay. Now we are going to integrate the equation. Okay. And for integration, we can say initially the bucket was at rest, the velocity was 0, and at the distance x the velocity is v. Okay. Similarly, the distance x initially was our L, and it stops at x. Okay. Therefore, it is quite simple. So from here we are going to get this as v square by 2 is equal to TL upon m, and this will be natural log of our x upon L. Basically that will be natural log of x minus natural log of L, and that will be giving us x upon L. Okay. And we know that the length of x is our less than L. X is our less than L. Okay. So there means our logarithmic unit will be our negative. Okay. Therefore we can say that v square will be equal to minus 2TL upon m, and we know x upon L we have taken as z. So we can write this as natural log of z. Okay. So this is our velocity. And then we can find out the kinetic energy as a function of the position, because we know our velocity at a distance x. So every calculation is based on when this bucket is at a distance x, so at this particular position. Okay. So we can write that kinetic energy, let us suppose it is over E, will be equal to over half m v square. Okay. And we can substitute our value of m as well as v, so we get this as our half, and m is our capital M multiplied by the ratio z, and our v square is our minus 2TL upon m and natural log of our z. And this 2 mass and mass cancels out, therefore we get that kinetic energy E, that is our function of our x, will be equal to minus TLZ, and we combine natural log of z. So we got our kinetic energy, and we are going to find out the maximum value of this kinetic energy. Okay. So obviously we are going to derivate it. So we can say our maximum kinetic energy. So we can say this is our dE upon dx. This will be giving us minus TL, and derivation is quite simple, so that will be our natural log of z plus 1, and we are going to set equal to 0, and therefore this tension and length cannot be equal to 0, so we get this as our natural log of z plus 1 is equal to 0, and from here we can say that our ratio z is equal to 1 upon E. So it means this maximum value of our kinetic energy, E max, will be equal to TL upon E. And what else? Okay, now we are also going to find out the momentum as a function of position. It means at a distance x. And here we have to remember that this maximum value of energy is independent of m, that's the mass of the sand. Okay. So it is not dependent upon this mass of the sand. And Then next is our momentum as a function of position. Momentum as a function of position, that is our P, or we can say this as our P of x will be equal to, let me write it here, so we can say that our P of x is equal to mass at the distance x multiplied with the velocity. And we already know all these, so this comes as m times z, and this comes as minus 2TL upon m, and this is our natural log of z and its square root. Okay. And so this is our value of the momentum. Okay. And we are going to maximize this momentum. Okay, let me sort it out. So we can write this as our P of x is equal to, you can write this as 2TL m square root, and this comes as our z, and square root of minus natural log of z. Okay, in this case we have to remember that intuitively it looks to us that this sign is negative inside the square root, so that will be giving us a, you can say, imaginary part of the result. But we have to remember this x is the ratio of x upon L, okay, and our x is always less than L. Okay, so this will be in turn giving us a positive result, okay, not a negative one. And let us maximize the momentum. So maximize the momentum, and we are only interested in this the function part. Okay, so let us call this as f of x is equal to our, we can just square it, that doesn't matter. Okay, and the square is going to sort out our square root, so we are going to get this as square minus natural log of z. So from here we get df x upon, okay, let me rephrase this because it is in z, so let me keep this in z, not x, otherwise it is going to keep, doesn't look good. So this is our z, z, z as well z, and this is also z, and we get this as our 2z minus natural log of z, which will be equal to our 0 and minus of z. Minus z is equal to 0. And so from here we can, because this ratio cannot be equal to z, so we can just take z as common and just ignore it. And furthermore we are going to get this as twice, and we are left with this minus natural log of z minus 1 and equal to 0, and this gives us, that is our z is equal to 1 upon square root of e. So this is basically our ratio, okay, and we can find out the maximum value by substituting z. Therefore we can say our maximum momentum will be equal to our TLM E and its square root. That is quite simple, okay, not big of the problem. So this was our second question, and we are going to deal with the third question. Third question is somewhat related to our this second question, but with a minor difference. Okay, Okay, I'll read out the second question, then we come to the difference part. So in this case, it is given that consider a setup. A massless bucket containing a sand is attached to the fixed wall by a massless spring that exerts a constant tension T. The bucket moves on the frictionless horizontal surface. Initial rest distance L from the wall. The sand leaks out at a rate proportional to the bucket's acceleration dm by dt bx square, double derivative, where x of t is the distance between the wall and m of t is the mass remaining in the bucket. Since the bucket acceleration towards the wall x is less than 0, and dm by dt is also less than 0, basically negative. So based on this, we have all these 4 questions, but here the key difference is how the sand dependence is there. In the first case, the sand dependence that over dm by dx was equal to over mass upon length. But in this case, we have this dependent upon our acceleration. Okay, this is the key difference between the second question as well as this, the current one. This is the third question. Okay. So first of all, let us say that our leakage, we can call this a leakage law also. Leakage law, and it gives us that our dm by dt is equal to b and the double derivative of x. Okay, that is our basically acceleration. Okay, it means if the bucket accelerates faster, the faster the sand is going to leak out. Okay, so it means the leakage depends upon the acceleration, not on the position nor time directly. Okay, so it is only dependent upon the acceleration. And we are also given that x is less than 0, so obviously the velocity will be also less than 0 and its acceleration will be also less than 0. Okay. And there will be only one force because we already calculated, so you can say the tension towards the wall and that is equal to force is equal to minus of t. Okay. And let us find out the mass as a function of time. Mass as a function of time. And for that, we can use that our summation of forces, obviously in the horizontal direction, will be mass into the acceleration. So the only force in the horizontal is minus of t, so we can say minus of t is equal to mass into our acceleration. Okay. Now we can use our leakage law, and that is our dm by dt is equal to our b, and remember this b is a constant. Okay. And for that, from here we can write that our acceleration is equal to 1 upon b dm by dt, and we can substitute it in the acceleration part. Therefore we get this as minus of t is equal to m upon b, and this comes as our dm by dt. And we can rearrange it. We get this as m dm is equal to minus bt and dt. And from here we can clearly see that the original equation of acceleration was basically a second order differential equation, and we converted it into first order differential equation, and that is going to help us to find out the solution easily. Okay, we can simply integrate it. So we can just integrate it, and we are going to get this as our m square by 2 is equal to minus bt, and this will be our t plus c. And we can use our initial condition, find out the constant c. So we have our initial condition, and initial condition we can say that at t is equal to 0, at the start we were having mass m, and therefore if you put in this equation, we get from here that this part becomes 0, so we get our c is equal to m square by 2, and therefore we can write the equation that our this we can say m of t is equal to, this becomes our m square, c is our m square. Okay, let me write it here, then we can, this is minus t plus m square by 2. So this gives us that m of t will be equal to, this is the m square, and we have minus 2bt into t square root. So this is mass at any given time t. And from here we can see that the mass is decreasing with time, but that decrease is not linear. Okay. We already know that from the given equation also. Okay. And this equation should be true. True means it should be valid. The square root should not contain the negative sign. Okay. So we can say that our m square minus 2btt should be greater than equal to 0, or we can say that our time t should be less than equal to m square upon 2bt. Okay. Under this condition only, our this mass equation is going to remain valid. Now we come to our part B. We are going to find out velocity as a function of mass as well as time. Velocity as a function of mass and time. And we are going to start from, once again, from the leakage law, and that law gives us that our dm by dt is equal to b, and we have double derivative of x, that is the acceleration, and this we can write as a b derivative of our velocity. And from here we can write this is equal to our dm is equal to b dv, and now we can just integrate it. Okay, and we know that our integration is going to give us our m is equal to, we have this as b v plus a constant, let us call that constant of c1, and we are going to find out our c1. So once again, our initial condition we know at t is equal to 0, our mass is equal to capital M, that is the bucket was full, and our velocity v was equal to 0. So based on this we can say that our c1, that constant c1 is equal to our capital M. Therefore we get that the velocity as a function of mass will be equal to, this becomes our m minus capital M divided by b. So this is the velocity, and we have to remember, because from this relationship we can also see that this velocity is negative towards the wall. Mass decreases, speed is going to increase. Okay, so this is our second part. Okay, not second part. Okay, we have to find out with respect to time also. Oh, that's quite easy now. Okay. So we are going to simply substitute this value of the mass which we have already calculated. We can say that our velocity as a function of time and that is our v of t. So we get this as our v of t. We already know this m we have calculated. Here it is. So we simply substitute this value. So we get this as our m square minus 2bt and its square root minus m divided by b. And this we can further sort it out, and we can say just before all sand leaves. Just before all sand means bucket becomes empty. So we can say just before all sand leaves, which basically means at value of m is equal to 0. And it means that when the all sand is going to leave, we get our velocity v is equal to minus m upon b. Okay, so it means the bucket reaches a finite speed when it is empty, okay, because it is only dependent upon our mass and the constant. Okay, so we can say that bucket reaches a finite speed when empty. Now we can find out also the position, that is value of x with respect to time, mass as well as time. So you can say position. Okay, this is part C, position as a function of time and mass. Function of time and mass. And we know that our distance x is equal to integration of the velocity. That is our simple solution. And we know v of t, we already calculated, so we substitute it here. And this integration is our, you can say the integration of our 1 upon b, and we have this as our m square minus 2bt into t square root, and let me take this 1 upon b outside, and minus m times dt. And so it is integration quite simple. So the integration of this m will be equal to mt. Okay. And the only typical part will be this one, so we can sort it out separately. So we can say that our m square minus 2bt and its square root. And for the sake of this, let us suppose that let our u is equal to m square minus 2bt into t, and therefore we can say that our du will be equal to minus 2bt into dt, or we can say that our dt is equal to our du, this is minus 2bt. So now we almost integrate it. We get this as our m square minus 2bt square root dt is equal to minus 1 upon 2bt integration, and this comes as u raised to power 1 by 2 du, and this will be giving us minus 1 upon 2bt, and integration of u will be over 2 by 3 u 3 by 2. So here 2 and 2 cancels out, and this gives us minus u 3 by 2, and this comes as our 3bt. And the second, this will be nothing but our m times t divided by b. So this gives us our minus m times t, okay, and divided by b, because v is along with it. So now we can simply substitute it, and therefore we get that our x of t will be equal to, this will be minus, and we have our, okay, we need to substitute u back. So u was our m square minus 2bt t. Okay, so we get this as minus, and we have m square minus 2bt t, and we have this as 3 by 2, and this is 3bt. Okay, and this is our the x of t. And oh, sorry, I forgot one thing. I forgot the constant integration. Let me write it again. So we get from here 1 upon b, and this is equal to minus, and we have our m square minus 2bt t divided by, this comes as our 3 by 2, 3bt, and minus mt, and this plus, let us call this as c2. We already used, yeah, that is called c2. Okay. And we can use the initial condition, or before that let me open the bracket. So I'm going to get this as our x of t will be equal to minus m square minus 2bt t 3 by 2, and this comes as 3 b square t minus m upon b times t plus c2. Let us come to our initial condition. Okay. So we can say that initially we know that our x of 0 is our L, okay, and at t is equal to 0, we get that our x of 0 will be equal to, this factor goes away, we are only left with our minus square 3 by 2 will be giving us m cube divided by 3b square t plus c2, and we can equate this is equal to our L. So therefore we get that our c2 will be equal to, this will be L plus m cube 3b square upon t. It means the final expression for our distance with respect to time will equal to minus m square minus 2bt t 3 by 2, and this is our 3b square t minus m upon bt, and we have a constant that is plus L plus m cube 3b square t. So this is our time dependent equation of our distance. Now we are going to find out position as a function of mass. Position as a function of mass, and we already know the relationship from part A. We know that our m square is equal to m square minus 2b t times t. from here we can say that our T is equal to m square minus small m square divided by 2bt, and we can put in the time dependent equation because everything will be in mass now. So we get this as our x of m is equal to, we get this as, this will be same, so we can keep it as it is, and then we have to solve this part. Okay, so if we substitute t, so this 2bt cancels out. Okay, so it's almost done, it's directly. So we are left with m cube minus m cube, and this is about 3b square t minus m upon b m square minus small m square divided by 2bt, and this becomes plus L plus m cube divided by 3b square t, and this term cancels out. So we got the relationship. X of m is equal to, we can write this as L minus m upon b, and one second, I missed something. Sorry, my mistake. We cannot cancel it. This is small m, not capital M. So we get this as the LCM will be same, so this will be 3b square t, and we get this as m minus m whole square and m plus 2m. Okay, so this is our mass dependent distance. Now we can find out our option number, part D. We have to find out the kinetic energy and its maximum value. Okay. So we know that kinetic energy, that is our E, is equal to over half m v square, and we already know the velocity in terms of mass. So we can say our energy is equal to 1 upon 2 b square, and this comes as m minus capital M whole square. We are going to derivate it with respect to mass m and equate equal to 0. So this gives us that our m is equal to capital M by 3. So maximum kinetic energy, V max, will be equal to 2m square, and this comes as 2 cube (27) upon b square. So this is our maximum kinetic energy. And now we come to momentum, part E. These are the small calculations, nothing much is there. So we have our momentum, and that is our P is equal to mass into velocity, or we can say 1 upon B m minus capital M. Once again, its maximization, that is our dP upon dm is equal to 0, giving us m is equal to m by 2. It means our maximum value of the momentum will be equal to m square by 4b. And finally, we are going to find out value of B, that is a part F, and we have to find out B so that bucket empties at the wall, and B is a constant. Okay. So we can say that we need to find out, choosing B so that bucket empties at wall. So it means we need that value of x is equal to 0 when our m is equal to 0. Therefore, we can put x of m is equal to 0. So we get this as 0 is equal to L minus m cube upon 6 b square upon t. So from here we get that the value of b is equal to, this will be our m cube 6lt, m cube 6lt and its square root. So this is the value of b. So these were the three questions. Okay. The first question was basically a combination of the projectile motion and some kind of friction. And other two equations, second and third questions, were based on the how the mass or the sand mass is going to change. Okay. And so this completes all the three questions. Thank you.